Hello, welcome to the next session on problem solving. Today we're going to work on problem 3.15 out of chapter 3. Problem states, in the figure, the rigid bar ABC is supported by the axial member, which has a cross-sectional area of 400 millimeters squared. An elastic modulus of E equals 70 gigapascals and a coefficient of thermal expansion of alpha equals 22.5 times 10 to the negative 6 divided by degrees Celsius. After load P is applied to the rigid bar and the temperature rises 40 degrees Celsius, a strain gauge affixed to the member 1 measures a strain increase of 2,150 microepsilons, which is our strain, right? Determine the normal stress in the member 1, the magnitude of the applied load P, and the deflection of the rigid bar at C. So this is a lot of information. It can be overwhelming a little bit. This is something that we have to extrapolate everything that we are given and then figure out how to apply it all to solve for these A, B, and C problems, or the question here. So the first thing that I do, and this is just my own note-keeping habit that I do, is it's just easier to identify the information if we kind of just take it out of the paragraph. So let's just go sentence by sentence and pull out what we know. What's the given information, right? And so we can just say given, right? So here we have a cross-sectional area, right? 400 millimeters of this member. So that's a cross-sectional area right here. So area equals 400 millimeters squared. Now, key note, this is millimeters squared, right? Millimeters squared, but what units are these in? Meters, right? So pay close attention to units. Units are very vital in this course. So the next says the elastic modulus is 70 gigapascals, or Young's modulus is E equals 70 gigapascals, right? So this might be a good time we can stop real quick and say, like, what is a gigapascal? What is a pascal? So a pascal, we want to mention a pascal is going to equal what? A newton, right? Because it's pressure, right? So a newton over meter squared, newton meter squared, and a megapascal equals a newton over millimeters squared, and a gigapascal equals 1,000 megapascals, right? Megapascal. Okay, so that's just a side note there. Next, we have a coefficient of thermal expansion. Alpha is 22.5 times 10 to the negative 6 divided by degrees Celsius. So alpha equals 22.5 times 10 to the negative 6 divided by degrees Celsius. So this is our given information, but there was another piece here that says, right, it says after load P is applied to the rigid bar and the temperature rises 40 degrees Celsius, right? So the temperature rise of 40 degrees Celsius, we don't know where it started, right? We could be 10 degrees Celsius originally, and then it goes up to 50 degrees. Who knows? Well, who cares? Well, all we care about is this difference, right? So we could say our change of, or our delta T, is going to equal 40 degrees Celsius. Now, why is this notation important? Because if we look at our actual formulas that were given, right, our formula, so we could say our strain in our thermal is going to equal what? It's going to equal our alpha delta T. Okay, and we have two components of that. The two components that we need already given to us. We can determine our strain due to the thermal expansion, or thermal expansion strain. So another piece of information we were given is our total strain, right? Our total strain, because a strain gauge affixed to the member measured the strain increase of 2,150 microepsilon. So what that means is epsilon total, and I'm just going to write epsilon tot, equals 2,150 micro epsilons, right? Which actually, because micro, if you look at the unit sheet that's on Blackboard, micro, right? So we can actually do and bring this up to, say, I don't know, millimeters, because we have millimeters here, we have millimeters here. So go ahead and multiply it to 10 to the negative third, right? Or negative sixth. 1, 2, 3, 4, 5, 6, yeah. So this can also equal, we can say 0.002150, right? And that's our epsilon total. And this will be millimeters divided by millimeters. So this is a lot of given information, right? So the first thing that we're asked is to find the normal stress in member 1, right? So the normal stress. Well, do we really just jump in and try to solve for normal stress? Well, we have to get to it some other method first. We have to use this information given and kind of work a roundabout way to get to there. So the first thing I mentioned before is we have already the given information to find our strain due to thermal expansion. We now have strain total. So what we could do is solve and determine what our strain for thermal expansion is and subtract it from the strain total to get the strain due to the load in member 1. Okay? And that's the thought process here. So what I'm going to do is zoom in a little bit here. And so what we'll do is epsilon total, solving for the thermal strain, right, is alpha delta T. So this is going to be, alpha was what, 22.5 times 10 to the negative 6. 22.5 times 10 to the negative 6. And this is divided by degrees Celsius multiplied to delta T, which is 40 degrees Celsius. And so epsilon due to thermal expansion then equals, plug it into the electric brain here, 22.5 times 10 to the negative 6th multiplied to 40. I get 0.0009. And this is a strain again, so it's unitless technically, but we're going to write it as millimeter divided by millimeter. So we can take our total strain, which is here, and subtract our thermal strain, and we get the strain due to the loading, the internal stresses in member 1, right? So this is E total equals E due to thermal expansion plus E, right? Solving this for E, or I'm sorry, epsilon, we get epsilon equals epsilon total minus epsilon thermal. So 0.00215 minus 0.0009, and I get our strain due to the internal forces of member 1 is equal to 0.00125 millimeters divided by millimeters. So all that work, and what did it get me? Yay, I got an answer. What does it mean? Who cares, right? So this answer is epsilon, but we need to go back to the formulas that we've used in the past, right? And epsilon, okay, epsilon equals what? It's delta L over L, which also we could say equals, it's our deflection over L, right? But we have another one, our Young's modulus equals what? Stress over strain, so sigma over epsilon. Or we can say stress equals Young's modulus multiplied to strain, right? So this is our first part of the question that we're looking for. If we remember, it says here, find the normal stress in member 1. So now, given our normal stress, we can just use this equation. We can say stress normal is going to equal our Young's modulus, which is 70 gigapascals, but remember it's not just 70 gigapascals. I did a little bit of work in the beginning just to front load this, right? So it's 70 gigapascals, okay? But a pascal is a Newton over meter squared. A megapascal we can call a Newton over millimeters squared, right? And then a gigapascal can be 1,000 megapascals. So 70 of these, right? So we could say 70 multiplied to 1,000 megapascals. This is our Young's modulus, right? And so then Young's modulus then equals 70 multiplied to 1,000, and then what is a megapascal? We can say it's a Newton over millimeter squared. So it's a Newton over millimeter squared. So that's, oops, 70. So 70,000 newtons over millimeter squared, right? So we can write here 70,000 newtons over millimeter squared, right? Multiplied to our strain, which was here our strain due to load. So this was due to load in member 1, right? So 0.00125 millimeters over millimeters. So the units, I kind of wrote out this because I was actually I'm sorry, in my head I was thinking about going somewhere else with this, but I guess we could have left that as megapascals or even gigapascals. That was just, I'm trying to do a little bit of work to keep the units in line so we can see this for another purpose, but it should work out just fine. So 70,123 multiplied to 0.00125, and I get 87.5. So what does that mean? 87.5. So stress equals 87.5 newtons over millimeters squared, which is equal to, it's 87.5 megapascals. And this is answer to part A. So you should write stress equals that. Okay? So now we learned that stress in part A, member 1, right? So if we go back up to the beginning of the problem statement, and it says here, find the normal stress in member 1, and then it says find the magnitude applied to load, or a magnitude applied of load P, right? So that's our next step. So I know the stress in member 1, but I have all this other given information, right? So the stress in member 1 is 87.5 megapascals, but what is stress, right? Stress equals force over area, right? So if stress equals force over area, then I could say force equals stress multiplied to area. And look at one of the given pieces of information that we had, right? Area, right here, area equals 400 millimeters squared. So we could say force equals our stress that we already determined in that part A, right here, which is 87.5 megapascals. So we can say 87.5 megapascals multiplied to 400 millimeters squared, right? But what is a megapascal? So we could say force equals, we can say 87, let's put it back into the units that I was thinking of before, newtons over millimeters squared, right? And then we could say 400 millimeters squared. Okay. And so we get 87.5 multiplied to 400 is 35,000 newtons. So the force equals 35,000 newtons. And this works because newtons is a unit of force, and millimeters cancel there, millimeters cancel there, millimeters squared cancels, and so we're left with newtons. So what is this force? This force is not P, okay? It's F. F from the stress that was applied to the internal forces of member 1. So let me zoom in here again on this figure. This is member 1, right? From D to B. Okay? That is not P. The force that's applied, right? So the stress of member 1, stress equals force over area of member 1. F does not equal P. Remember that. Okay? What is F? F is that force. Now, let me zoom out again, go back over here. Let me draw a free body diagram. Maybe that will help explain it. So now we have this member here, right? And I have some reactions and some forces that are occurring. We can draw P at the end here, right? So this is P. I can draw the force of 35,000 newtons. We can just call that, let's draw it positive. Let's always assume positive. So it's forces up that way. And then I have a couple of reactions that are occurring over here. So I have a reaction of AY, and then I have a reaction of AX, right? And then we have some distances from here to here is what, 1.75 meters, and then from here to here is what is it, 1.25 meters. 1.25 meters. Okay, so now how do we use our tools of statics to be able to solve for this? We're looking for P, right? So let's just go ahead and sum the moments about point A, right? Which puts those to 0, and then we'll just have F and P to deal with. So sum the moments at point A equals 0. Identify that this is going to be the direction of positive, right? So F is going in a positive direction because F is going counterclockwise around A. And so it's going to be F multiplied to 1.75. P is going counterclockwise, so it's going to be minus P multiplied to this whole distance here is 3, and all that equals 0. Solving for P, P equals F multiplied to 1.75 divided by 3. Plugging that into the calculator, 1.75 divided by 3. So I get the magnitude of P equals 20,416.67 newtons, right? Or we could just approximate this, you know, P approximately equals, we could say 20.4 kilonewtons. Okay, so that's part B. Let's zoom back out and zoom into here. So we've got part A done, part B done. Now the deflection of the rigid bar at C. So the deflection is going to talk about if this, right, is the rigid bar, right? We want to care about how much it has deflected down this way. Does it deflect down here? Does it deflect way down here like this? Or how far down did this thing move? Okay, because it isn't stationary. It's actually due to the loadings, both thermal expansion and the load P. It has shifted in some measurement down. Okay, we're going to figure that out now. So let's go over here and use, well, I'll do some blank space, I guess. So if we know this distance, right, and we'll just call this, we'll call this A, and this B, and C, and what do we know about deflection? What is deflection? Out of the given information, out of everything that we've done so far, how can we find deflection? So we know the stress in member 1, we know the force of P, we know the force at B, or so the force at member 1, we know the strain of member 1, right, which is here. So what do we know about strain? What's this guy? I wrote here, let me zoom in on it, I wrote strain is this, right? So we could say strain equals, or delta L over L, right? So we can find how much it actually deflected, how much it actually changed in length to be able to create that much strain, right? Okay, so let's go ahead and do that. So our epsilon, right, 0.00125. So we'll just do it here. So epsilon of member 1 equals 0.00125 millimeters divided by millimeters, right? And so with this, we could say that epsilon equals our change in length divided by length. So multiply epsilon to length, so epsilon length equals our change in length. So 0.00125 multiplied to, oops, real quick, let me write my units. Millimeters divided by millimeters multiplied to, what's the length of member 1? It's actually, go back up to the problem statement, 3.75 meters, right? 3.75 meters. So we need to change that to millimeters. So 3.75 meters, changing that to millimeters is 1,000 millimeters per 1 meter, right? And then this is going to equal our delta L. Plugging that into calculator. I take that back, I was wrong. This is the wrong epsilon. Not just in the loading of 1, right? It's the load in 1, the entire, due to the entire loading. So it's not just, I take that back, I sorry leading you astray. So it's not just the load, the epsilon due to the forces, it's the entire epsilon, the entire strain, which is going to be both due to the thermal expansion and due to the loading. So I apologize for that. So it's going to be twice what it was before, right? Or almost twice. So 0.00215. So let's go back here. 0.00215. 0.00215. Okay. Hey, I make mistakes too, right? It's a tough class. So this, solving this out with the correct epsilon, right? Because it should be epsilon total, right? And then you should get a change in length that equals 8.0625 millimeters, right? So that change in length, right, 8.625 millimeters, okay, that's a pretty big change in length. So what does that mean? That means that from B, right, so if I draw this out here, let's just draw a line there, I could say that here, from here to here, is that 8.0625 millimeters. Okay? So then here to here, what's that distance? Well, you could use a couple of different methods. You could use similar triangles, right? Because look, this is a one triangle, and this is another triangle, right? And there's that distance. You could figure it out there. Or you could use trig, right? I like trig better. That just makes more sense to me. So I'm going to use that method. It's both ways you'll get the same answer. But say let's figure out this angle here. This angle, we'll call it theta. And this distance between A and B is known, which is 1.75 meters, right? Is it 1.75? Yeah. So we could find that distance and go, say 1.75 divided by, or as you were, we could say, what is it? Sine theta equals opposite, okay, it's tangent, right? Tangent theta. So tangent theta equals opposite over adjacent. So theta equals tan inverse of opposite over adjacent. And plugging in the values of these triangles, you should get theta equals, I got 1.79. We got theta equals 77.754 degrees, right? So since now we know the distance between A and C is 3, right? So A and C is 3. To find the distance here for this, it's going to be 3 tangent theta equals that deflection, right? So 3 tangent of 77.75, I get 13.821 millimeters equals the deflection at C. And that should be the final answer. Okay. Kind of made a mistake on that one. I apologize for that, but this should be at least an indication that, you know what, everybody sort of kind of does what they can, and you just make a mistake and then you just go back and try it again. All right?